Welcome to the Deep Dive. Today we're tackling something truly mind-bending from the world of physics. Imagine matter that doesn't just repeat its pattern in space, like a crystal lattice, but repeats its pattern in time, like a clock that ticks forever on its own. We're diving into the fascinating concept of time crystals.
It's a pleasure to be here. Yes, time crystals. A really exotic idea, first seriously proposed by Nobel laureate Frank Wilczek. Our goal today really is to unpack this. How do they seem to bend the rules of physics as we know them? And why is there so much excitement right now?
Right. So think of this as your shortcut to getting up to speed on some seriously cutting-edge science. No PhD required, hopefully.
Yeah.
Let's start with the basics. We all kind of get ordinary crystals, diamonds, salt, snowflakes, atoms locked in a repeating spatial pattern.
Exactly. A periodic structure in space.
So how does adding time into that periodic structure work? What does that even mean?
Well, think of it this way. A time crystal takes that spatial periodicity and adds a temporal one. It's a quantum system, crucially, where the particles are arranged periodically in both space and time. And here's the kicker. This repeating motion happens even when the system is in its absolute lowest energy state, its quantum ground state.
Okay, hold on. Lowest energy state usually means things stop moving, right? Everything settles down. How can it have motion?
That's the truly bizarre and fascinating part. It's what we sometimes call motion without energy, because it's already in its ground state. It fundamentally cannot lose any more energy to its surroundings. It can't settle down any further.
So the motion is the ground state.
Precisely. Its natural lowest energy configuration is this state of perpetual periodic change. It's not getting energy from somewhere secretly. This internal rhythm is inherent to its ground state.
And this relates to breaking symmetry, doesn't it? Ordinary crystals break spatial symmetry. The pattern looks different if you shift it a bit.
Correct. They choose a specific arrangement in space, even though the underlying laws of physics don't prefer any particular spot.
So time crystals break. Time symmetry, time translation symmetry.
Exactly. They spontaneously adopt their own internal clock or rhythm, oscillating periodically, even though the laws governing them are constant over time. They don't follow the external beat, so to speak.
Okay, but does that mess with fundamental laws, like thermodynamics? Isn't that sort of perpetual motion-ish?
Good question. It sounds like it, but no. It doesn't violate the laws of thermodynamics. Energy is conserved in the total system. Importantly, its entropy, a measure of disorder, doesn't decrease. It actually remains constant over time in this state. It's a stable, non-equilibrium phase of matter. Very different.
Wow. Okay, so it's theoretically possible, but has anyone actually, made one in a lab?
Absolutely. That's where things get really exciting. We now have experimental proof, specifically for what are called discrete time crystals, or DTCs.
Discrete.
Meaning they typically exist in systems that we periodically kick or drive externally, maybe with laser pulses. And the key signature, the smoking gun, is that the system responds by oscillating at a frequency that's a fraction, a subharmonic of the driving frequency.
So if you poke it, say, twice a second, it might respond by changing its state only once a second.
Exactly like that. It picks up its own internal rhythm, slower than the external drive. It remembers the beat, but marches to its own slower drum.
I do remember hearing about some big experiments a few years back.
Yes, 2016, 2017. There were landmark papers from two independent groups almost simultaneously, one at Harvard, led by Mikhail Lukin,
Okay.
and another at the University of Maryland, led by Christopher Monroe. Both used different setups involving quantum spins, but both clearly showed this stable subharmonic oscillation that really solidified the field.
Right, proof of concept. But science moves fast. What's happened since then? Have they gotten better, more stable?
Oh, dramatically so. There was a really significant leap reported in February 2024 from researchers at Dortmund University in Germany. They created a time crystal using a semiconductor material, indium gallium arsenide. And get this, it maintained its time crystalline state for 40 minutes.
40 minutes? That sounds huge compared to before.
It's enormous, nearly 10 million times longer than the previous records, which were fractions of a second. And crucially, it didn't seem to be decaying. It potentially could have lasted much longer.
Wow. What does that kind of longevity let you do or see?
Well, it opens the door to studying much more complex behaviors. And indeed, very recently, just in March 2025, the same group at TU Dortmund reported observing really intricate dynamics, things like fairy tree sequences and devil's staircase patterns emerging in the time crystal's behavior. These are complex, almost fractal-like patterns in how different rhythms can lock together.
Okay, that sounds pretty deep. Fractals in time almost. But stepping back, what's the potential payoff? Are these just cool physics experiments, or could they be useful?
That's the billion-dollar question, maybe literally. One of the most promising avenues is quantum computing. You need stable quantum bits, or qubits. Time crystals, with their incredibly stable inherent oscillations, might offer a way to store quantum information that's robust against the noise that usually plagues quantum systems.
So, like a super stable quantum memory.
Potentially, yes. It's early days, but their inherent stability and periodicity are very attractive properties for that kind of application.
This is genuinely fascinating stuff. We've gone from a wild theoretical idea to lab realities that last for ages and show complex behavior, potentially pointing towards new technologies. It really feels like time crystals are a fundamental shift in how we think about matter, energy, equilibrium, even time itself.
I agree, they challenge so many assumptions. And it really makes you wonder, doesn't it? We found a way matter can spontaneously break time translation symmetry. What other fundamental symmetries of nature might be out there, waiting to be broken in ways we haven't even imagined yet? What other utterly new forms of existence might that reveal?
A truly provocative thought to end on. Thank you for guiding us through this deep dive into the world of time crystals.
My pleasure. It's a privilege to talk about it.